If you can really internalize the story of the carbonyls, then you're going to have a pretty good chance at conquering any carbonyl reaction thrown at you. Humans are storytelling animals. If we really want to become an OChemNinja, we have to find a way to unify all of these reactions that we're learning, rather than just trying to memorize another reaction in a list. If we can find a unifying story that guides all these reactions, then we can have a chance of becoming a good OChemNinja. This is especially true for the Carbonyl unit. Carbonyl unit is one of the more challenging units for students in the entire course. I have a separate video linked down below that explains why. In the Carbonyl unit, we're not just learning reactions additively, we're learning reactions multiplicatively. Every reaction is really learning 6 or 7 reactions at the same time. So we need a story that unifies the Carbonyl unit to make it easier to understand, that gives us something to hold on to so we have a chance at succeeding in this unit. Over the years, I've developed what I call the story of the Carbonyls. It's like a good children's book series you read when you were growing up. The story was pretty much the same every single time. You kind of knew what you were getting when you went in. If you can do the same thing for carbonyl reactions, you pretty much know where you're going to go as soon as you start. The story of the carbonyl is a story in 4 chapters. Stay tuned where I go through all 4 of these chapters in detail. Chapters 1 and chapter 4 pretty much occur in every single mechanism. Chapters 2 and 3 we'll see are somewhat optional. So just like your favorite children's book series, the plot changed a little bit every time, even though the overall story arc was pretty much the same for every book. If you can really internalize the story of the carbonyls, then you're going to have a pretty good chance at conquering any carbonyl reaction thrown at you. Let's start with chapter 1. Every carbonyl mechanism has chapter 1 as part of its story. Chapter 1 goes something like this. Carbonyls are electrophiles. When you think of carbonyls, the first thing I want you to think of is that carbonyls are electrophiles. They're electrophilic at the carbon, and they're electrophilic toward good, strong anionic nucleophiles. This is the major mode of reactivity for carbonyls, and I have a separate video on major modes of reactivity that I'll link to down below. So whenever I see a carbonyl as the starting material for a reaction, I know in my heart that it's going to be attacked by some kind of nucleophile. That's why carbonyls exist in this course. That's their main character trait. They are electrophilic and want to be attacked by nucleophiles. They're electrophilic toward good, strong anionic nucleophiles. So after I see a carbonyl, I look over at the reagents. If I have a good, strong anionic nucleophile, the nucleophile can directly attack. For example, we might have a carbonyl reacting with sodium borohydride. Sodium borohydride is a good, strong anionic nucleophile. Chapter 1, nucleophilic addition. The hydride can directly attack the carbonyl and kick electrons up onto oxygen. That's nucleophilic addition. The same is true for acyl substitution. If we're making an ester, the methoxide group can directly attack the carbonyl because it's a good, strong anionic nucleophile, kicking electrons up onto oxygen in a nucleophilic addition step. Sometimes, in order to complete chapter 1, we need to make the good, strong anionic nucleophile. This may seem weird, but you've almost certainly seen this before. This is not necessarily a new concept. One example is a common example is the Grignard reaction. In order to do a Grignard reaction, we often have to make the Grignard reagent by adding magnesium to an alkyl halide. An alkyl halide is not a good, strong anionic nucleophile. Not a nucleophile at all. But when we add magnesium, we turn it into a good, strong anionic nucleophile so that we can do chapter 1, the nucleophilic addition. This is not uncommon. Don't get too confused about turning some functional group into a good, strong anionic nucleophile so you can do chapter 1. But what if we get to chapter 1 and we don't have a good, strong anionic nucleophile? Instead, we have a weak neutron nucleophile. This is also not a big deal. We add an acid to make the electrophile more electrophilic so that even a weak neutron nucleophile can attack. An example of this would be something like ester hydrolysis, where we have an ester and we add an acid so that we can make the carbonyl more electrophilic so that even weak neutral water can attack. And when water attacks, we're doing chapter 1, the nucleophilic addition. I'm going to skip ahead to chapter 4 right now because pretty much every carbonyl mechanism has chapter 1 and chapter 4. Chapter 4 is proton transfer to the end. It's where we neutralize the molecule, we make our final product, we just clean up any charges that are remaining in the intermediates. An example of this is we often have an O- charge that we need to add some kind of acid quench to protonate the O- to make a neutral alcohol. H3O+, water, generic H+, NH4Cl. It doesn't really matter which acid quench we use, we're just cleaning up the charges to make the molecule neutral. Other times we have a positively charged intermediate and we need to remove a proton to make the positive charge back to neutral. This is common in acetal formation and other acid-catalyzed reactions. Every mechanism has chapter 1, the nucleophilic addition of the carbonyl. It's kind of the whole point of carbonyls in this unit. And most every mechanism has chapter 4, some kind of proton transfer to the end to neutralize the molecule and make the final product. Chapters 2 and 3 are optional. Not every story has chapters 2 and 3 as part of their mechanism. Chapter 2 I like to call the Proton Shuffle. It's after we've added the nucleophile, we have to ask ourselves, why did I just add that nucleophile? Well, I kind of want it to stay. But sometimes when we add that nucleophile, it turns out it's the best leaving group, and I don't want it to leave right away. So chapter 2 is the Proton Shuffle. I take the proton off the thing that I want to stay, and I put it on something else that I want to leave. We shuffle the proton from one group to another. We make the group that we added not the best leaving group, and we make something else the best leaving group. We see this in mechanisms like the ester hydrolysis. After we've added water, Water we just added, we want to stay, but right now water's the best leaving group. So we take the proton off of water and put it on something else to make something else the best leaving group. We also see this in acetal formation. After we've added the first equivalent of alcohol, we kind of want it to stay, but right now that alcohol is the best leaving group. So I shuffle the proton. I take it off the alcohol that I want to stay, and I put it on to water that I want to leave. This is proton shuffle. Not every mechanism has a proton shuffle, but when we do, we're changing something else into the better leaving group. Chapter 3 is also somewhat optional. Not every mechanism has Chapter 3 as part of its story. Chapter 3 is leaving group expulsion. If, after I've done the nucleophilic addition, there's some kind of leaving group in the molecule that's not the group that I just added, then the electrons will collapse back down from oxygen, kicking out that competent leaving group. We see this in reactions like the ester formation. When the methoxide attacks, the electrons go up onto oxygen. Now I can collapse those electrons back down and kick out the chloride as a competent leaving group. Another example where I see this is acetal formation. After I've done the proton shuffle, I collapse electrons down from oxygen to kick out the water leaving group that I just made. This is another example of leaving group expulsion. Finally, we also have the example of Grignard addition to an ester. When I add Grignard to an ester, the electrons go up onto oxygen. I have a competent leaving group, the OMe-. The electrons can collapse down from oxygen to kick out that OMe- in a leaving group expulsion. One caution here in Chapter 3. Like any good children's series, not every story is exactly the same all the way through. And this is true in Chapter 3. After I do the leaving group expulsion, I remake a carbonyl. And for some mechanisms, the nucleophile can add a second time to that carbonyl. Sometimes it adds a second time to form a new product. Sometimes it adds a second time, but it's not really a productive step. And sometimes it doesn't add a second time at all. So we'll have to learn some of the nuances of some of these reactions to figure out how exactly Chapter 3 plays out each time. And those are the 4 chapters of the story of the Carbonyls. I've gotten pretty good at this. I can go through the whole story in my head. You should practice until you can get pretty good at going through the whole story in your head. I like to do it as a series of question and answers. Why do I have a carbonyl? Well, because I want to attack it by a nucleophile. Sometimes I have to make the nucleophile. Sometimes I have a good strong anionic nucleophile. Sometimes I have a weak neutral nucleophile, and I need to add an acid catalyst to make the electrophile more electrophilic, so even a weak neutral nucleophile can attack. Once it attacks, why did I have that nucleophile attack? Well, because I want it to stay. Sometimes it's not the best leaving group, but sometimes it is the best leaving group. So I do a proton shuffle to take the proton off the thing I want to stay and put it on the thing that I want to leave. Why would I make a better leaving group? Because I want it to leave, so I can do it a leaving group expulsion. Electrons collapse down from oxygen to kick out that leaving group. Sometimes the nucleophile can add in a second time, though. In all cases, though, after I do these chapters, the last step in these mechanisms is some kind of proton transfer to the end, cleaning up the charges, making the molecule neutral to make the final product for these carbonyl mechanisms. This is the story of the carbonyls. Let me show you some examples. One example is the sodium borohydride reduction. This is a fairly simple story. We do the nucleophilic addition of sodium borohydride to an aldehyde, and we do proton transfer to neutralize the charge and finish the product. 2 chapters, pretty straightforward. Another example is cyanohydrin formation, also fairly straightforward. We do the nucleophilic addition of the cyanide to the carbonyl, make an O-, proton transfer to the end to make the final cyanohydrin product. This is also a very simple story. From here, we can start to increase the complexity a little bit, but it's still the same story. For a Grignard addition, we're going to do a good strong anionic nucleophile adding to the carbonyl, but we have to make that nucleophile first. So we make the Grignard to do the nucleophilic addition, proton transfer to the end, makes the final product. Same thing for the aldol addition mechanism. The enolate is a good strong anionic nucleophile. I just have to make it first by deprotonating an alpha proton. After I make the enolate, nucleophilic addition to an aldehyde makes an O-, and then I can do proton transfer to the end to make the aldol addition product. When I do an ester reduction with lithium aluminum hydride, I first start with the nucleophilic addition. LAH is a strong anionic nucleophile, can directly attack the carbonyl to make an O-. I could do a proton transfer at this point, but I'm not there yet. I need to do chapter 3 first. I have a competent leaving group, so the electrons collapse back down from oxygen to kick out the competent leaving group. That forms a carbonyl, and the nucleophile adds a second time. Hydride adds a second time to the carbonyl, electrons up onto oxygen, nucleophilic addition to make an O- charge, and then proton transfer to the end to make the final alcohol. Even our most complicated mechanisms, the ones that feel really scary to us, can really be broken down into these 4 chapters. Take the acetal formation reaction, often a historically confusing reaction for students. Still follows the same 4 chapters. I have a carbonyl, I want to attack it with a nucleophile, but I have a weak neutral nucleophile, so first I need to add an acid to make the carbonyl more electrophilic so that even a weak neutral nucleophile can attack, nucleophilic addition. Once I do the nucleophilic addition, that alcohol that I added is the best leaving group, but I want it to stay. So I do a proton shuffle. I make the alcohol not the best leaving group, and I make water the best leaving group. Why would I make water the best leaving group? So that it can leave in a leaving group expulsion step. That reforms a carbonyl, and the alcohol does attack a second time to form the acetal intermediate, and we do final proton transfer at the end to make the acetal. Chapters 1 through 4, right in order. Same thing with the Fischer esterification. It's still the same 4 chapters. We have a weak neutral nucleophile, so we add an acid to make the carbonyl more electrophilic, so even a weak neutral nucleophile can attack in a nucleophilic addition step. Once I add that nucleophile, I want it to stay, but right now it's the best leaving group, so I make it not the best leaving group, and I make something else the best leaving group. Why would I make something else the best leaving group? So it can leave in a leaving group expulsion step. Final proton transfer to the end makes the ester. Same story. So there we go. All of the entire carbonyl unit can be summarized in one carbonyl mechanism, the story of the carbonyls. I went through actually most of the reactions in this unit in this video, but I didn't go through all of them. But all of them pretty much do follow this story of the carbonyls. There's only a few exceptions. One of those exceptions is the Wittig reaction. The Wittig reaction does not follow the story of the carbonyls. But I have a separate video on the Wittig reaction I'll link to down below. We can see that it is still highly predictable, even though it doesn't follow the story of the carbonyls. If you can internalize the story of the carbonyls, then you have a really good chance of being an OChemNinja in the carbonyl unit.
I'm glad you're here with us for this training today. Check out these other videos in my playlists to see if there's anything else that can help you level up your ninja levels even further. As always, don't forget to like and subscribe.